Hello everyone, welcome to screencast number 2 on colligative properties. We just finished talking about boiling point elevation, and so in this screencast we will be talking about freezing point depression. So with freezing point depression, we know that freezing will occur when the vapor pressure of the liquid equals the vapor pressure of the solid. So since the vapor pressure is lowered when we have a solution, the freezing point will also be decreased. Less energy is needed by the system to reach that equal vapor pressures, so therefore freezing temperatures are decreased. We use sodium chloride and calcium chloride often to de-ice roads. And the reason why is because in order for molecules to freeze, they need to become more ordered, they need to cluster together. And what happens is the solute molecules, the Na and the Cl or the calciums and the chlorides, they're going to get in the way in between the solvent. So the solution or the solutes in the solution sort of get in the way of the molecules of the water for freezing. So therefore you need less energy for that freezing to occur. So the formula for freezing point depression is very similar to the boiling point elevation. It's the change in the freezing point, and that's going to equal I, Van Hoff factor, times molality, times the freezing point constant for whatever the solvent is. So let's do a little example for freezing point depression. How much ethylene glycol, C2H6O2, must be added to 6 liters of water to depress the freezing point to negative 15 degrees Celsius? So, our first step would be to calculate the molality. So in order to calculate molality, I use the freezing point depression calculation, or the formula, and I just rearranged it to solve for molality, which is right here. So the molality equals the change in the change in temperature of the freezing point divided by I times the constant for water. And now the constant for water is 1.86 Kelvin times kilograms per mole. So we're just going to plug in those numbers. We have 15 degrees for the change in temperature because we're going from pure water, which is going to freeze at 0 degrees Celsius, to negative 15. And the I constant is going to be just 1 because ethylene glycol is a non-electrolyte, times our constant for the water, which is 1.86. So our molality is 8.06. So step 2 is to calculate the mass of C2H6O2 from molality. So we have molality equals moles of the ethylene glycol over kilograms of the solvent. So if we look at our given, we are given 6 liters of water, which then I can calculate out for the bottom, for the denominator, using the density. 6 liters of water is going to be equivalent to 6 kilograms. And we're going to calculate the number of moles of the ethylene glycol. Okay, so we're going to take the 8.06, and from that we're going to multiply it by the 6 kilograms to give us number of moles of ethylene glycol. So we have 48.4 moles of ethylene glycol. Now once that we have the amount of moles of ethylene glycol, we just can convert moles of ethylene glycol to grams of ethylene glycol by multiplying by the molar mass of ethylene glycol. So the molar mass is 62.8 grams, so we end up with 3,004 grams of ethylene glycol. Okay, so for this slide, what I wanted to show you is just the phase diagrams of a solution versus the phase diagram of a pure solvent. So what you see right now in the black solid lines, that would be the phase diagram for the solid. Your green dotted line that's going right there, now that's going to be your phase diagram for your solution. And then your solid is for S, that's a solid phase, your liquid for L, and then your G for gas. So if you notice that you have a lowered freezing point depression for the solution right here, and if you look at the pressure at 1 atmosphere, you see where the boiling points are. And the boiling point of the solution, the green dotted line, the temperature is going to be higher than the boiling point of the pure solvent. And finally, if you compare the vapor pressure between the liquid and the gas, the vapor pressure for the solution, the green dotted line, is lower than the vapor pressure of the pure solvent.